we are now in the final part of CVAAS and HGAAS. I will show you slides on the disadvantage and advantage of each method. Hydride generation is very advantageous for metalloids, as stated here, because these are the elements in the periodic table that can generate hydride upon reaction with the reagents. And because of that, it will give you low detection limit because this method is selective. The keyword is selective because they are the ones that can do this hydride generation, even though you analyze these metalloids with other transition metals or alkaline earth metals which cannot generate hydride. Therefore, they can only be detected, whereas the other one will not be detected. Okay, because it is very selective, means it is very limited application only. Okay, if let's say you are working in a QCQA line, this is not a problem because you are going to analyze these metalloids only and only that for a longer period. But if it's in an R&D line, then hydride generation might give you limitation. Other than that, hydride generation AAS, okay, sometimes can produce the formation of analyte hydride, okay, that will be suppressed by a number of common matrix components and will give you chemical interference. Okay, this chemical interference will be discussed in the next few slides. Cold vapor mercury, the best is for mercury. Okay, cold vapor mercury, mercury analyzer. Okay, this come way before ICP-MS comes. Okay, now the preferred method is ICP-MS. ICP-MS is not covered yet. It's going to be learned in several weeks more. But before ICP-MS come, okay, CVAS is sort of like the golden method. Okay, the golden method until it is accepted in ISO method of choice, because it gives you 100% atomization due to the production of the cold vapor. Okay, as I mentioned before, mercury can be volatile at room temperature. So if you are using anything that is having heating, you will not get 100% sampling efficiency. But with cold vapor mercury analyzer, you can get this. Okay, all of the mercury placed in the reaction will be completely atomized and transported, therefore giving you detection limit down to around 20 ppb. Okay, however, it is only limited to mercury only. Okay, this is not a problem for one of our potential customer in pusat perkhidmatan analysis, whereby the analysis is only like mercury. For several years, they only send samples for mercury analysis. So having cold vapor AAS in our lab is actually beneficial to us. It's very making business because of the sample that is specific for mercury only. Okay, but nowadays it is having competition with ICP-MS instrument. Okay, in terms of cost, CVAS is way cheaper than ICP-MS. Okay, and also sometimes the disadvantage is that we may have background or contamination from the reagent system as well, because we have apparatus, right? We have apparatus and then you mix up, and then we have flow injection over here, flow injection system. So all these things must be cleaned now and then. Okay, so these are the standard methods stipulated in ASTM, and you can also find in AOAC method. Okay, means that atomic absorption spectrometry is well accepted for the past 40 or 50 years, and now is still being used. Okay, you can find this file, okay, in the internet. I'm not sure whether you can find the free one, but there is one ASTM website that sell all this standard method. Maybe when you go outside and work later, you have to have this kind of document, and you may need to buy the documents because sometimes your lab want to comply with the standard method, so you have to follow everything. Okay, so that's what happened in our pusat perimeter analysis in C19 level 4. We have to buy the APHA method, okay, several of them, and we have to buy AOSC method because we have to comply with the standard method. Okay, now we go to the interference that may happen in atomic absorption spectroscopy, be it in flame, be it in graphite furnace, or CV, or hydride generation. Okay, we have non-spectral and spectral. Okay, for spectral interference, you can imagine that the interference must come from the radiation source. Okay, because radiation source is the one that is giving you spectra, right, for the atom to absorb. Okay, but spectral interference is relatively easily curable, okay, because we can put apparatuses such as continuum source background correction or Zeeman background correction. Later we'll give. But for Zeeman background correction, I'm not going to explain much. I'm going to focus on this because this is really complicated, and this actually require like one topic altogether. Okay, but just to make sure you understand, this one is also sufficient. This is extended one. Okay, and then we have non-spectral interference. We have matrix interference. Okay, easy to be understood. And then we have chemical interference. It is coming from your analyte itself. And we have ionization interference. Let's go one by one. We start with spectral first. Okay, the spectral interference come to the radiation overlapping from the light source. Okay, remember in atomic absorption spectroscopy, the light source is HCl or EDL. Okay, hollow cathode lamp or electrodeless discharge lamp. Okay, and it is specific for each element. It is specific for each element. So virtually, the interference from spectral is almost none. But it may rise up, okay, because of the general background radiation from the flame. Okay, means that any other element or solvent ke sample that may be inside your sample together with your analyte may want to absorb the radiation as well. So that's what we call as sort of like spectral interference. But if you have interference radiation very significantly, okay, for some reason, sometimes the hollow cathode lamp just start to die and so on, we have a correction, what we call as using alternative wavelength. Okay, each element, they do not have only one absolute wavelength. Okay, they can go inside the HCl lamp. As I mentioned before, we have a cathode, right? Okay, it will excite and emit. When it emits, it can emit radiation for the analyte to absorb at several wavelength line. Okay, that's why for each element, sometimes they have 2 or 3 wavelength. Okay, I will show you. For example, over here, copper, you can use longer wavelength for detection, but at longer wavelength, the sensitivity might reduce. Okay, as for lead, we can use either 283.3 or 217 nanometer. Okay, let us see on the table. Okay, this is the standard atomic absorption condition for PB. The ultimate wavelength to be used is this one. Why? Because of the detection limit that is good for the analysis. But if 283.3 is not giving you the sensitivity that you that you want because of certain reason. Okay, sorry. The best one, sorry, this one 217, because the lowest detection limit is 0.1. I'm sorry. Okay, if 217 is not good for you because of the spectral interference, you can opt for the second wavelength, still giving you detection limit that is reasonably low. Okay, and you have other options as well. Okay, but you see the concentration is getting higher, means that only concentrated sample analyte should be used. And then after spectral interference, which is also related to spectral interference, is background interference. In background, okay, this is not background correction, this is background interference, sorry. In background interference, this usually happen when detector, okay, detect other signal. Siapa ada signal tu? Okay, interference can come from everywhere inside the system. Okay, sometimes imagine that a bulky system contain a lot of complicated lines and all those spectral interference also coming in. So what we can do, the simplest one is for you to do blank analysis. Dah belajar kan blank analysis? Blank analysis is whereby you prepare a solution containing all your solvent, whatever, buffer, whatever you do, except there's no analyte. That's the meaning of blank. No analyte in blank. Means that you want to know if there any, if let's say you want to analyze PB, is there any lead when I do blank? Okay, if let's say you have lead inside blank, it is coming from the system. It's either spectral interference or leftover or anything that we absorb, giving you the same wavelength at the same giving you the same signal at the same wavelength. But if you detect blank, if you detect lead even though you run blank, that's not a problem, because you can always set to a signal of 0 after you correct. That's what we call as corrected signal. Sometimes you ada dapat data, right? It shows you corrected signal, means that the instrument deduct the blank signal of PB siap-siap. Okay,